So, if you could remember in the last chapter, in the last lecture, we had completed the derivation of the signal to noise ratio at the output of angle modulators uh, or angle demodulators, and it came out to be this equation, or you could write it in various other forms. You could also write it in this form. Now, what are the insights that we gain from these equations that express the signal to noise ratio at the output of the receiver in terms of signal to noise ratio at the uh, input to the receiver, or the signal to noise ratio of the baseband communications? So, first thing is that in both PM and FM, the output signal to noise ratio is proportional to the square of the modulation index. So we can very well see in this equation that both for PM as well as for FM, all right, so actually I have a power supply shortage, so there might be some problems in the lecture, which I will try to overcome them because there is no electricity right at this point in my house. All right, so you could very well see that the signal to noise ratio at the output is directly proportional to beta, which is almost non-existent in AM communication, because you could see in angle modulation you have this directly proportionality. So even if your signal to noise ratio at the baseband level is less, but if your beta is high, you can get good signal to noise ratio at the output. Even with low signal ratio at the baseband level, by having high value of beta, you can get greater SNR at the output. But let us see what happens in amplitude modulation. You could see in amplitude modulation, I have a power problem, so I will just take Bismillahirrahmanirrahim. I hope you can hear my sound. Uh,
जी सर, आ रही है आपकी आवाज़।
all right. So I hope all of you can hear my sound. Aji, can everyone hear my sound?
जी सर, आ रही है आवाज़।
अच्छा, मुझे पता नहीं मैसेज आ रहा है कि आई एम
यस सर,
बीइंग
आ रही है
म्यूटेड.
आवाज़।
अच्छा, चलो ठीक है. All right. So I think the screen is also being shared. All right, so I was trying to explain you this point, the difference between angle and amplitude modulation. So this you could see here that as you increase beta, synchronous ratio at the output of the angle demodulators, they increase. But let us see what happens in AM. Now you know in AM, for example, if you have double sideband suppressed carrier or you have single sideband, synchronous ratio at the output is equal to synchronous ratio at the baseband level. Or in conventional AM, which is used for radio broadcast, or you have double sideband with carrier, in that case, you know your synchronous ratio at the output is equal to this efficiency factor times the synchronous ratio at the baseband level. All right, where we know A is this value. So, and we know that synchronous ratio at the baseband level is the baseband communication, which is the received power of the signal at the input to the receiver divided by the noise power. So you can see that in both conventional or in single sideband, you don't have any factor like beta factor, which is coming inside these expressions of signal-to-noise ratio at the output level. So you cannot basically increase your signal-to-noise ratio at the output level for an AM system as you can increase it in a PM system by the help of the beta value. Second point is that the increase in the receive SNR is obtained by increasing the bandwidth. So greater the bandwidth, you have greater signal to noise ratio. So in angle modulation, you can provide a trade-off between bandwidth and transmitted power. Now why this happens, you can also see here, because we know that from the Carson's rule, bandwidth is given as follows. Then you know this bandwidth expansion ratio is given as follows. You just take W here on this side. So you can see beta comes out to be this thing. This we have studied in the last lecture also. So this expression was also there in the book, that the signal to noise ratio at the output level can also be expressed as follows. So this shows us that if you increase your bandwidth expansion ratio, the signal to noise ratio will actually increase. All right. This we also saw in the book here in the last lecture. Signal ratio at the output is directly proportional to the bandwidth expansion factor. Greater this factor, greater will be the signal to noise ratio at the output. So if you want greater power for angle modulation systems, you can increase the bandwidth. Hence, you will get greater signal to noise ratio at the output. So we get a trade-off between bandwidth and transmitted power. So you increase the bandwidth and you will be getting greater power. But again, this is not possible in AM systems. In AM system, you know, you had fixed bandwidth. It could be W, it could be 2W, or it could be some bandwidth somewhere in between W and 2W, but you could not trade off between the bandwidth and the transmitted power. Now, what is the third point? The relationship between the output SNR and the bandwidth expansion factor is quadratic relation. So we could very well see that this has a quadratic or square power, quadratic equation, and information theory results from a theoretical perspective that what is the optimal relationship. The optimal relationship has to be an exponential relationship. Optimal relationship should be exponential, then it will give us the best results. But we have a quadratic relationship which is far from the optimal relationship. Next point is that can we increase SNR indefinitely by increasing beta? We just saw that if you increase beta, your SNR increases. Can we do this till indefinitely? We'll be able to, till infinity we can do this, that we are increasing our beta and hence we are increasing our signal to noise ratio. No, we cannot do it indefinitely, or we cannot do it till infinity, because the noise power will start to increase. First of all, I will try to explain this with the notes and then we will come back to the book. But not indefinitely, we cannot do that, because after a certain value of beta, what happens? Because, you know, as you are increasing your beta, your bandwidth, Carstens bandwidth, which is 2 beta plus 1 into W, is increasing. Now, as your bandwidth or Carstens bandwidth or your occupied bandwidth for FM and PM is increasing, which means we have more noise power. Because, you know, what is noise power? We saw that the power spectral density of noise was equal to this and this for PM and AM. But we also saw that what is the noise power? Noise power, you have to integrate these power spectral densities over the BC bandwidth. So for PM, it comes out to be this into BC, and we saw earlier. And for FM, it comes out to be BC cube over this thing. So greater the bandwidth, your noise power is increasing. So as you are increasing your beta, your bandwidth is increasing, your noise power is increasing. Now, what there is a problem that as your noise power increases, all our calculations were based on the very important relationship that signal power is very much large as compared to noise power. But if your noise power is very large in itself, then your signal power is not that large as compared to the noise power. So all of our approximation will not hold. Especially this approximation that we actually made for our calculations. That that the noise power, there is something missing here, that the noise voltage is probably the noise voltage is much less than AC is equal to 1. So noise voltage is much less than AC. That will no longer hold, provided the noise V and T becomes very large because of increase of beta. So in fact, this means we cannot increase beta indefinitely. Okay, and there is a threshold. So there is a threshold, okay, up till which we can increase our beta. We cannot increase our beta indefinitely. So at a certain point, increasing beta will become harmful and that will deteriorate the system. So we will be discussing this in detail afterwards. So another point is that the SNR in amplitude modulation increases if we increase the transmit power. Because if you increase the transmit power, the receive power will increase. When the receive power increases, you know the output SNR will change. Same thing also happens in angle modulation, as you could see in the formula, but the mechanisms by which this increase is happening is totally different. So you could see here that signal to noise ratio at the output will increase if transmit power is increased because PR will increase. Because we know signal to noise ratio at the output of a signal ratio at the output of AM system, you could very well see it was PR over N naught W, or you know some factor multiplied with this PR over N naught W, where PR and over N naught W is the signal noise ratio at the baseband level. So signal noise ratio was directly proportional to signal noise ratio at the baseband level, both for amplitude modulation and you can also see for angle modulation. Signal noise ratio at the output is again directly proportional to signal noise ratio at the baseband level. So both of them are proportional, both for AM as well as for angle modulation. They are both proportional. But you could see the mechanism is different because once we are increasing power in AM, so we are definitely increasing power in PR, because if you increase power in amplitude modulation, this means that you are increasing the carrier power, and that will definitely increase the PR power. But FN and PM, increase in transmit power does not lead to increase in signal power, but it results in decrease in noise power. All right, because you can see noise power is inversely proportional to AC square. If you are increasing AC, okay, this means you are increasing your noise power, because you know the message signal is actually contained in the phasor part. So if you are increasing the power in FM system, you are not increasing the power of the message signal, because the message signal is contained in the phasor part. You are increasing the carrier amplitude and power. That results in the decrease of the noise power. Hence, the signal to noise ratio increases. While in case of AM systems, you could very well see that once you increase the power of the transmit power, so you increase the transmitted signal's amplitude, and that directly results in the increase in the transmitted power. As you can see in the various relationships, your receive power will be increasing because your transmit power is increasing, and hence your signal to noise ratio will increase. In angle modulation, the message is in the phase. That is why it will not affect, but it will affect because the noise power decreases. So increase in transmit power does not increase the demodulated message power in case of angle, but in case of amplitude it increases. But SNR increases for both the cases, because in AM the signal power is increasing, while in FM or PM the noise power is decreasing, resulting in a signal to noise ratio being increased for both the cases. Now the sixth effect, we saw that in FM especially, the effect of noise is higher at higher frequencies. So you could see the noise power is increasing, or you could see actually the PSD was directly proportional to F square for PM systems. So greater frequency means you have greater noise, PSD, power spectral density of noise is greater for higher frequencies. So signal components at higher frequencies will suffer more from noise than signal components at lower frequencies. So in some applications where we use FM to transmit, for example, signal sideband FDM signals. So each channel is signal sideband, and then all the bands, let us say, are frequency multiplex. So you know the in single sideband the bandwidth is just W, and after every W we have placed a new channel that will be called SSB FDM. All right. So in this type, those channels which will be at higher frequencies, they will have more noise. Okay. So we need to compensate, and that compensation is done by pre-emphasis and de-emphasis, which will be discussed later. So let us see this example. In this example, he says what is the required receive power when beta is this, W is this, and N naught is this, and the normalized message signal is 0.1, power of the normalized 0.1. So, and the required SNR after demodulation is 60 dB. So you can see in the book, but I have also done this in the notes. So we have this relationship. Which was actually derived earlier. You could see here this relationship for FM. In FM system, we have this relationship as I saw. So in this relationship, you could very well see you are given that required is 60 dB. You are given beta. You are given the normalized power. You're given N naught. You're given W. You just have to find the received power at the input to the receiver. All right. So you put all the values. 60 dB will become 10 to the power 6. Dividing by 10 becomes 6, and 10 to the power 6. And hence you can find the receive power, the input of the receiver coming out to be 2 into 10 to the power minus 5. Now we saw earlier in one of the insights that we gained from the mathematical derivations of the signal-to-noise ratio or the output of the angle demodulator that there is a certain threshold. You cannot increase your beta above that threshold, because if you increase the beta above that threshold, the noise power becomes so high that the assumption that the signal power is much greater than the noise power will not hold. So we will be studying that threshold effect or that relationship. So we had assumed earlier that the signal to noise ratio is high at the input to the demodulator, and with that assumption we had actually observed that the signal and noise components at the output of the demodulator are additive. So if you could see in the last lecture when we were solving, so you could see that the signal to noise, this was a signal part, this was a noise part, and they all came out to be in the additive form. Actually, we had used this assumption. Once you can use this assumption and you do the relevant mathematics, you can come up with this relationship where the signal and noise are additive. All right. But now what is the case? But this assumption of high SNR was a simplifying assumption, so that we could simplify the mathematics for non-linear modulation. You know that modulation and demodulation is actually a non-linear process, so we were just simplifying uh, it by we simplified our calculation by using our assumption. But actually, you know what happens, because you have a non-linear nature of the demodulation process, the additive signal and noise components, we know the signal and noise is actually adding at the input of the modulator. They actually do not result in the additive signal and noise components at the output of the demodulator, because you know the channel is the actually, you know, this should also be the demodulator, because you know signal and noise are being added uh, additively in a simple addition manner at the input to the demodulator, but at the output of the demodulator they might not result in additive signal to noise components. They result in additive signal to noise components provided we have that assumption. If we do not have that assumption, then this will not be correct. Then this assumption will not hold. We won't say that the signal and noise are adding in an additive fashion at the output of the demodulator. At the input they are additive, but at the output they are generally not additive. They are additive only and only when the signal to noise ratio is high. The signal and noise are completely missed in a single process by a complicated nonlinear relationship, so they will not come out to be having a simple additive relationship. You know, by meaning an additive relationship, we have seen that there are three types of models. So you have seen nonlinear, uh, time varying, then we have LTI, and then we have a simple, you know, signal plus noise. So simple signal plus noise will only hold the, you know, the AWGN channel, which we saw earlier in chapter 1, will only hold if the signal ratio is high. Otherwise it will not hold. Only under high SNR, this non-linear relationship can be approximated as an additive form. Otherwise, it cannot be approximated. At low SNRs, signal and noise they get intermingled, and we cannot recognize the signal from the noise. So therefore, the SNR cannot be defined. So this is the threshold. Threshold is the point where the noise becomes large, or where signal noise ratio decreases, and if the beta increases above the threshold value, or in other words, if the SNR, the signal ratio at the input of the demodulator, it decreases below this threshold, SNR, then the signal mutilation will occur, or you can say the signal and noise will not add in an additive fashion. So basically you can define this threshold in two ways. One thing is that your beta cannot go above certain beta, and all the reasons are there, because greater beta will lead to greater noise power, and all that will lead to greater bandwidth. This will lead to greater noise power. Hence your SNR assumption will fail. And you can also define this in terms of the threshold SNR. All right. So if your SNR decreases beyond a certain threshold, this means that the signal to noise ratio is small. It is not large. And if it is not large, you will not get an additive signal to noise relationship. All right. So You can define the threshold in terms of two ways, in terms of beta and also in terms of SNR. In terms of SNR, this will be called the threshold SNR. If the SNR coming into the demodulator comes out to be less than the threshold SNR, the additive assumption will fail. Okay? Or if the beta comes out to be greater than the beta threshold, we can also define in terms of beta threshold, then what will happen? The noise power, the bandwidth is so large, the noise power becomes large. Again, our assumption will fail. So this threshold places an upper limit on the trade-off between bandwidth and power. So we saw in FM systems or in angle modulation systems that you can, more power was directly proportional to the bandwidth expansion factor or directly proportional to beta square. Okay, but we have a threshold. You cannot increase the beta above a certain value, so you cannot increase the power above a threshold value because all the assumptions will fail. This limit is a practical limit in the value of, yes, it will also limit the beta value, okay, as we have seen all this explanation. Now the derivation of this beta is quite involved and it is out of the scope of our course or analysis. We will just use those analysis and get see those results from those analysis. We will not go into the analysis, we just see the results. And from those results, we will try to design our FM systems so that their outputs have an additive signal to signal and noise. Signal and noise are adding at the output of the angle demodulators. So what are those relationships that come after the analysis, which is beyond the scope of our course? So now we know synchronous ratio at the baseband level for baseband communication. This we saw also in AM systems. This will be the same thing that's defined in FM systems. This we also saw in the last lecture also, that the synchronous ratio at the baseband level is given as follows. All right, so this is the first definition, that the synchronous ratio of the baseband level threshold. The threshold synchronous ratio is defined as 20 beta plus 1. How this relationship comes, this is not in the course. We just have to see this relationship. All right. So whatever your beta is there, your threshold will be defined as 20 times beta plus 1. This means the signal to noise ratio at the baseband level, or you can, in other words, you can see at the input of the demodulator, this must be greater than this threshold. Signal ratio at the baseband level, or S over N over B, or this value, okay, must be greater than this threshold. Okay, so now we can get two-way problems and both could be solved. For example, if I am given the value of PR, all right, so let's also see in the notes here so that we could that I've also explained all the points. So another angle of understanding, the synchronous ratio at the output is directly proportional to the bandwidth expansion factor square into synchronous ratio at the baseband level. All right. Now, after the analysis that is out of the scope of this book, we just saw that this threshold, so the threshold, the synchronous ratio threshold, at the baseband level. So your baseband signal must be greater than this threshold. The threshold is given by 20 beta plus 1. Okay. Now at the same time, we know that this threshold is also equal to PR and not over W. All right. Now, your S over N beta B has to be greater than this threshold. But if I just want to evaluate at the threshold level, assuming that my PR over N naught is equal to the threshold, I will get the maximum amount of beta that is allowable in my system. All right. So I take this value of signal to noise ratio and equalize this with the threshold equation. Okay, and if I solve, I will get this beta. So I will get the maximum amount of beta that I can use, because if my beta is greater than this threshold, then this threshold beta, ये threshold beta आएगा आपके पास इस equation से, then you can very well see then your signal to noise ratio threshold will also increase and will become greater than the signal to noise ratio at the baseband level that you are actually getting, and hence your additive assumption of signal and noise will not hold. So by using this relationship, if I'm given the received signal power at the input of the demodulator N naught W, I can find the maximum amount of beta that I am allowed to work with. So my beta must be less than this threshold beta, than maximum amount of beta that is allowed. So that if my beta is less than this allowed, then you know this threshold will be less than the received signal to noise ratio. Hence, you will be working with the signal ratio will be high, and you will be working with the appropriate assumptions that the signals and noise, they are added in an additive fashion at the output of the demodulator. Vice versa, you can also use this equation. You know that from the Carson's bandwidth, the bandwidth of angle modulated systems is equal to 2 beta plus 1 into W. All right. Let us say you are given some value of the bandwidth of FMAM, and you're also given W. You find this beta, but you will make sure that this beta is less than the beta threshold, or the beta threshold that you have found from this equation, because it comes out to be greater than this threshold, then the additive noise and signal assumption will not hold. Right? So yes, you want to use as much greater value of beta as possible, because you know greater value of beta means that the power requirement on the system has decreased. You're using more of your beta is greater. This means you have more bandwidth, as much as bandwidth you are using, and you don't have to apply very high signal to noise ratio at the baseband level or at the transmitter, and you will be getting still a signal to noise ratio at the output which is above your requirements. But at the same time, you have to make sure that your beta does not cross the beta threshold. Are all of you are understanding? This is a quite subtle point. अच्छा, हाँ जी सलमान साहब, are you understanding? Salman Jameel, are you understanding this difficult point? लगता है उनको आवाज़ नहीं जा रही, पता नहीं आजकल बिजली का भी बड़ा मसला हुआ है। हाँ जी, हाँ जी हमजा, आर यू अंडरस्टैंडिंग दिस डिफिकल्ट पॉइंट?
जी सर, मैं सुन तो रहा हूँ, लेकिन मैं थोड़ा सा आपका लेक्चर्स लैग कर रहा हूँ तो इस वजह से प्रॉपर्ली भी अंडरस्टैंड नहीं कर पा रहा।
अच्छा चलो ऑलराइट। पता नहीं अब बाकी रोल नंबर्स मुझे इतने नहीं याद है जिनको। रोल नंबर 144, कैन यू हियर मी? 144, पता नहीं कौन से स्टूडेंट्स हैं कि नहीं है, ये भी बहुत दफा। रोल नंबर 145, कैन यू हियर मी? रोल नंबर 145, रोल नंबर 145। अच्छा, एक तो काफ़ी स्टूडेंट्स पता नहीं होते हैं तो शायद वो कुछ कह भी नहीं सकते
सर वो
आजकल।
लाइट का इशू ना हो, लाइट का
लाइट की
इशू
इशू तो
मे बी
हमारे
सर।
यहाँ भी बहुत बुरा आया है, इस वक्त बिल्कुल बिजली नहीं है, बस अल्लाह करके
जी
लेक्चर
सर।
दे रहे हैं किसी। चलें खैर, ऑलराइट, सो लेट अस कम बैक टू द लेक्चर। हम कहाँ पे थे? Alright, so just to you know recap what we have studied. So for a given bandwidth, we find an appropriate beta, and then using the relationship, we determine the minimum receive power to make the whole allocated bandwidth useful. So this means that we have these two things that we have to take care. One is this relationship, alright, there's a threshold, and then we have this relationship. So we have to take care that we are operating with respect to both. You will be choosing beta with respect to this, given BC and W, but you also have to make sure that for that beta which you have chosen, you are getting a threshold, your signal noise ratio at the baseband level is greater than this threshold. So you're doing certain examples, and I hope this subtle or difficult point becomes clear. So you could see the limitations. So limitations on channel bandwidth from the the Carson's rules, and then we have the limitation because of this threshold effect. Both are to be considered. So figure 6.5 shows this relationship. You could see here, this is the signal to noise ratio for various values of beta, and you could see here that if you increase the signal ratio of the baseband level, the signal noise ratio at the output is generally actually increasing. For double sideband and single sideband, we have already seen that the signal ratio at the output is equal to signal noise ratio at the baseband level. So if you are increasing this, they have a linear straight line relationship because they are exactly equal. A straight line with 45 degrees. But for FM systems, the signal ratio at the output, it comes out to be some factor multiplied by signal ratio at the baseband level, as you can see here. So signal ratio at the output is equal to some factor times the signal ratio at the baseband level. So it is giving you more value than signal ratio at the baseband level because you are multiplying this, all right, with beta PMN square. This will be definitely greater than simple signal noise ratio at the baseband level. Or you could also talk in terms of dBs. So you could see that for FM or PM systems, you are getting greater value of signal ratio at the output as compared to signal ratio at the baseband level. But in DSB and SSB, you're getting a straight line, they are both equal. But here, they will be greater. But yes, they are greater. But you could see here, at a certain point, there is a drop off or threshold effect. This is threshold, this is threshold, this is threshold. Because at these points, your signal ratio has decreased as compared to signal ratio given by the threshold. So hence, you will not be getting the additive signal to noise ratio or the relationship that we have, you will not be getting that relationship. That relationship holds here when you are above the threshold. So threshold is apparent when certain drops in the output SNR. So these plots were drawn when the average normalized signal power was given as half. Again, some of the steps are missing, so you can see in my notes here. So we have this relationship as we saw earlier from this equation we saw. The signal noise ratio is given as follows for PM. For FM, it is 3 times. And rest is almost same, BP and BF for FM and BP for PM. So we use this relationship for FM. Signal noise ratio at the output is equal to this times signal noise ratio at the baseband level. Alright, at the output is equal to this times the signal noise ratio at the baseband level. Meaning at the baseband level at the input of the demodulator. So if I choose my PMN, which is the average message power as half, so in this case signal ratio at the output comes out to be 3/2 into this. This same thing he has written here. All right. Let us take some example of beta. Let us take beta is equal to 5. All right. So some of the steps are missing in the book, so I will refer it to my notes. So if I take beta is equal to 5 and I put beta is equal to 5 in this equation, and I take it 10 log or decibel on both the sides. So 5 squared 25, 75/2, 10 log over 2, and this 10 log S7 and beta. So for beta is equal to 5, what I am getting? I am getting output signal noise ratio at the output of the demodulator in dBs is equal to 15.7 dB plus signal noise ratio at the input to the receiver in dBs. All right. Now let us check the threshold equation. As the threshold equation, we know what is the threshold. We know the threshold is given by signal noise ratio beta threshold is 20 beta plus 1. And as we have chosen beta is equal to 5, you can see that my beta threshold comes out to be 120, or my beta threshold in dBs comes out to be 20.8. So 120 log comes out to be 20.8 dB. Now you can use this equation. You will be getting 15.7 gain in addition to the signal noise ratio of the baseband level. But the important thing is that your signal noise ratio at the baseband level must be greater than this threshold. If it is not greater than this threshold, you cannot get 15.7 gain. You will not be getting this relationship, and you will be not getting this much gain. Okay. So we must have the signal ratio at the baseband level, okay, must be greater than 20.8. He says, let us say the signal ratio at the baseband level is 20 dB, but we know 20 dB is less than the threshold. So if the input to the signal ratio at the input of the demodulator is less than this threshold, then sorry, you will not get this 15.7 gain in addition to the gain at the baseband level, because the threshold, your signal ratio at the input is less than the required threshold. Now, all right. I use beta is equal to 2. All right, no problem. If I use beta is equal to 2, then you know synchronous ratio at the threshold, which is again the same equation, 20 into beta plus 1, threshold comes out to be 17.8 dB. You have decreased your beta, the threshold decreases. Now if you are using 20 dB, the 20 dB is greater than 17.8 thresh dB, and hence now you will get the additive relationship, and now you will get a gain. In this case, you can very well see that the input signal ratio, which is 20 dB, is greater than the threshold for beta is equal to 2. So now you can use beta is equal to 2 because the required value is less than the value that you are getting at the input. If you use beta, this is the output signal ratio at the output of the demodulator, which we just saw was 3 over 2 beta square, 3 over 2 beta square S over n, 3 over t beta square S over n. So you will get your SNR output as equal to 6 times S over n beta. Now you can use this equation because your synchronous ratio at the input of the motor is greater than the threshold, and then you apply 10 log of this, you will get 7.8. So you will be getting a gain of 7.8 above the synchronous ratio at the baseband level. So you know baseband level was 20 dB. So you will be getting 7.8 plus that 20 dB, because we assumed the signal ratio of the baseband level was 20 dB. So you'll be getting an additional gain of 7.8 above the 20 dB gain. This was all about the threshold effect. We can also define a single equation that can incorporate both the threshold effect and the signal to noise ratio. So how can we do that? We can use this equation, the threshold equation. The threshold equation, 20 beta plus 1, inside this equation. So the value of beta, the value of threshold, which is 20 beta plus 1, from the threshold equation can be substituted here. This will become 60 beta square beta plus 1 into PMN. You will get 60 beta square beta plus 1 PMN. So this relationship will incorporate both the things. It incorporates the beta threshold equation, 20 beta plus 1. It also incorporates the signal to noise ratio at the output of the angle demodulator or FM demodulator, provided you have a additive signal to noise relationship at the output of the demodulator. So this is the same equation. We put this value in 6.2.2 and you will get this relationship. Now let us see some example. So we have an FM system and we require that the SNR at the receiver is 40 dB, and we require the minimum amount of transmit power. We want the SNR at the output of the receiver to be 40 dB, but we want to send minimum amount of transmit power. This means we want to maximize our beta. So if you maximize beta, you maximize the bandwidth, and hence you will be requiring minimum transmit power, a minimum signal ratio at the baseband level. But again, the constraints are there that the bandwidth of the channel is 120 kilohertz, the bandwidth of the message is 10 kilohertz, and this average to peak power ratio of the normalized message signal is half, and not is given. What is the required transmit? All right, this is and from this constraint, we want to find the required transmit power, or the required power at the transmitter, if we know the channel is attenuated by 40 dB when it passes through the channel. So you can also see it from my notes. So first of all, we have the Carstens rule. We are given beta C, 120 kilo. We are given W, which is 10 kilo. From that, we find our beta is equal to 5. But we have to check that this beta must be less than the beta threshold. If it is less, then no problem, we can very well use it. Okay. So you can see we cannot increase our beta here, because in this question we are being constrained by the value of BC and W. Okay. We actually want to maximize beta as much as possible, because as much as possible you're able to maximize your beta, you will be able to send the signal with the minimum amount of signal to noise power. All right, that is what he has said, that we want to minimum amount of transmit power. What is the minimum? So for that we need to maximize our beta, but at the same time we cannot increase our beta indefinitely. All right, so here you can see that our beta is being constrained by available BC and W. You cannot increase your beta greater than 5 even from the Carstens rule, because if you increase your beta, you know that the required bandwidth will increase. If you increase your beta with respect to 10 kilohertz, it will become greater than 120 kilohertz, which is given, which you cannot do that. Again, you are being constrained by 120 kilohertz. We just have to check that with this beta is equal to 5, which is the maximum I can go according to this constraint that I am already given. Am I working above the threshold, or I am not working above the threshold? So we have to find the threshold. All right. So this was the equation that we actually found just earlier, where we combined the additive signal to noise ratio at the output monitor with the threshold equation. This comes out to be this thing. So in this equation, we are given that the signal ratio at the output has to be 40 dB. PMN is given to be half, and we need to find this beta value. So I solve this equation. You can solve this. So beta square beta was going to come out to be 333, and you can use various values of beta so that the right and left they become equal. So here you can see that beta comes out to be 6.6. So now we have seen that with this constraint with this constraint and this constraint, uh, my beta or the beta threshold is 6.6. So your beta cannot go greater than 6.6 because this is the maximum allowable value of. So you can go up to 6.6. You can decrease the power by going up to 6.6, so you will be requiring less power. But here you can see that my beta is already constrained by 5, which is less than beta. So 5 is a good value. It is less than the threshold value, and I have to use 5 because if I go above 5, my Carson bandwidth will increase, which will not specify the industrial requirement. And if I go less than 5, then I will be requiring more transmit power, which I want to have the minimum value of the transmit power. So I will compromise and I will use beta is equal to 5, which is less than the threshold and which is the maximum possible value that I can go under the bandwidth constraints. Alright. So my bandwidth is less than 6.5, so we have to choose just 5. After choosing this 5, I know I'll be above the threshold, and once I know I'm above the threshold, I can use the additive equation. Signal ratio at the output in additive fashion is equal to this thing, and I put this value of 5 here. I know this value, so I can find signal ratio at the baseband level. So at the baseband level, signal ratio comes out to be this value. At the output, we know it's 10 to the power 4. You can solve this. Signal ratio at the baseband level comes out to be this much value, and then once I know signal ratio at the baseband level, which is equal to PR over N naught W, I can find the receive power, which will be this 266 into N naught W, N naught W, which is given. This is W given and not given. This comes out to be my receive signal. This much watts, and in dB it will come out to be the same value. Then what is the transmit power? Transmit power, this is the receive signal, then the transmit power has to be 40 dB plus, because 40 dB is the attenuation of the channel, so 40 dB plus, you will get this much dB. This comes out to be, you can take it inverse dB, it's 266 watts. So you have to, the minimum amount of power under these constraints is to be 266 watts, so that you will receive this much signal at the this will be the receive signal power at the input of the demodulator. The signal ratio at the input of the demodulator will be this, and hence your output will come out to be 40 dB. Here you could also see in this example that let us say I had no bandwidth constraint. The constant bandwidth constraint was not there. You are not constrained to 120 kilohertz. You could use as much bandwidth as possible. Then I would have chosen 6.6 because this is the maximum I can use. All right. So above the threshold value or up to the threshold, I will use 6.6. And if I use 6.6, you can very well see the signal ratio at the output will be actually more of it will be covered by beta. You will require less power at the input to the receiver, and if you will calculate the signal ratio at the baseband at the input to the transmitter will come out to 153 instead of 266, and similarly your PR will come out to be 0.0153 in comparison to 0.266, and transmit power comes out to 153 in terms of 266. So less power will be required at the transmitter if you are working at the threshold. The next point is pre-emphasis and de-emphasis. So as we have seen in the relationship that especially in case of FM, the output PSD is directly proportional to the frequency we saw here, and not ACF square. So that is why greater frequency will have greater noise. So, but the signal, that doesn't change, but the noise increases. And this was all because of the differentiator at the FM. So how to compensate for this increased noise power at higher frequencies? So what we do, we increase the high frequency components prior to FM modulator at the transmitter, and we send the higher frequency components which will be facing higher frequency noise, which will be facing high power noise at higher frequencies. And this can be done by passing at the transmitter, by passing the signal through a pre-emphasis. You can see pre-emphasis, you are increasing the signal amplitude. For greater frequencies, we have greater signal amplitude. In other words, you can say this is a high pass filter. This is called the pre-emphasis filter. Thus, what will happen, that the noise massive signal will have greater power, and the degradation will be reduced. Now, once we have increased the high frequency signals, the massive signal has changed. So you need to restore them. So we perform pre-emphasis. There was de-emphasis, we perform firstly it was pre-emphasis, now we form the inverse proportion operation of pre-emphasis, that will be called de-emphasis. So we will de-emphasize the higher frequency components and will emphasize the lower frequency components. So exact inverse operation will be performed. So we will pass, previously we passed it to a high pass filter, now we will pass it to a low pass filter. This cascade has a reciprocal frequency characteristics, you can see here. So one is directly and one is 1 over the same factor. So in cascade, the overall effect to the signal will be nullified by using the pre-emphasis and the de-emphasis filters. So he's saying in commercial FM radio broadcasts, we use low pass and high pass filters. Low pass for de-emphasis, high pass for pre-emphasis, and time constant is 75 microseconds. Frequency response is given as follows for de-emphasis. So the cutoff frequency can be calculated from the time constant. It comes out to 2100, and this is the 3 dB frequency of that industrial filter. Analyze the effect of pre-emphasis and de-emphasis on the overall signal noise ratio in FM broadcasting. You can very well see that for the signal part, the transmitter and the receiver, they cancel the effect of each other. Pre-emphasis and de-emphasis, they cancel the effect of each other for the signal part. But for the noise part, the noise is just at the receiver. So it will be just facing a de-emphasis filter. Alright. So what will be the PSD at the output of the de-emphasis filter? At the output of the de-emphasis filter, the PSD will be the PSD of the FM, which was N0 AC square F square times the square of the filter response of the de-emphasis filter. So de-emphasis filter amplitude response was this thing. So its square will be square root cancels. All right. So it will be this thing. This is the power spectral intensity of the noise. So how can I find the noise power? I will just integrate this over the bandwidth. Of the massive signal W. So I integrate this. Again, some of the steps are missing. So you can see in the notes here. So we needed to integrate this thing, f square into this is, square of the de-emphasis filter. So we know this from the integration tables. So this could be written as follows, and now you can apply the table here. Table apply, you will get this thing. Apply the limits, and this W will be added. This will be also added, so you will get this as the noise power of the noise at the output of the de-emphasis filter. So the advantage of using a pre-emphasis and de-emphasis becomes apparent if you take the synchronous ratio of the output of a pre-emphasis de-emphasis and divided this by the synchronous ratio of the output of a simple FM. So the signal power, it's same in both the case. It will cancel. Its noise power will come here, and its noise power will come in the numerator. So they will be inversely proportional. Now you can put the value. This noise power is this, as we have just found. The noise power for an ordinary FM without pre-emphasis and de-emphasis we found in the last lecture. So, AC cancels, T2 cancels, and you get this relationship. So you can see here that the signal to noise ratio by using a pre-emphasis and de-emphasis will be this factor times signal ratio at the simple, and this factor will be greater, cube power. So you can see the advantage of using the pre-emphasis and de-emphasis. So he also gives an example here. We can see in the book, this is easy. So all the things are given. We are given F0, we are given W, we are given beta. So you want to see the improvement in the output of M when we use pre-emphasis and de-emphasis. So the improvement is given as follows. So this equation actually relates SNOPD over SNR. So first we find this ratio. We can find this thing. Multiply this thing with S over N at the output of a simple FM, which does not use pre-emphasis and de-emphasis, and we have seen that for simple we have 3 beta square PMN into S over N beta. You put the value that this is you can see here that by using beta is equal to 5, you are getting 15.7 gain over the signal ratio at the baseband level. But use pre-emphasis and de-emphasis, then signal ratio at the output times this thing, because the ratio is equal to this thing, so this comes here, and this comes 21.3, 13.3 dB. So whatever the signal ratio that you are getting at the output of the simple, this will be plus 13.3. So this was 15.7 plus 13.3. So you will be getting a gain of 29 over the gain of the signal ratio at the baseband or at the input of the demod. Instead of 15.7 for a simple FM, by using pre-emphasis and de-emphasis, you will be getting a gain of 29. So the time is up. I will just end the lecture here. This section 6.3 is very small that we will take 4 or 5 minutes in the next lecture. So we will postpone its study for that lecture. I will end the lecture. Sorry for all the disturbance that still is there because of this power failure in my area. Thank you very much.